Hi everyone, this is Raju from Smart AI Technologies. Welcome back. Today we're going to see a concept called how to brighten the low light images using deep learning. I think you can see on the screen where I implemented it on one image which is captured by NASA. When I feed that image, the output image you can see like the darkness behind the main image, that is the black hole is removed, and we can clearly see the black hole stuff and also stars behind it. You can change the image. We'll check with it. We'll upload some other images now. You can see the results. I think here this was the original image, and this one is the enhanced image. In enhanced image we increase the brightness of an image where the dark background is removed, and we can clearly classify what are all the objects are there in the image. In this project we will going to build a deep learning model which will exactly give results like this. We will start from importing the dataset to building the dataset. You can see, okay, now itself I executed the model, and we will encounter so many type of losses. We will analyze the model, our model, with all those losses, and we will implement it on some images where you can see like this. Okay, this was the original image. PIL auto contrast is a library which is freely available to increase the contrast of the image, but the enhanced image is that enhancement done by our model. So our model enhancement is far better than the PIL library enhancement which is already available. Now we will discuss few of the application of this project. So the first thing is e-commerce. Under e-commerce, you may be knowing they will be having clear images in their website of a product, but in reality when they click the images they will be having darkness behind it or a disturbance behind it, like that. Okay, but each image is being edited and that has been updated into the e-commerce site. It will consume a lot of time and it requires some expertise. It means it consumes time and also money. Now what if you have a model where you can directly push the images, okay, and you will get the result where you can directly make it into your e-commerce site. It will save time and also money. So the next thing is space, and when it comes to space, the most of images when we capture they will be having black background, okay, with some bright light images. Now in that condition our model works fine because it is well built to remove the blackness or darkness and make it bright. So if we use our model in space related images as I shown before, we will get good result. And the third one is medical images. Under medical images also, in some situation or some cases we will get some images with some blackness or some low light. In that case we can feed that result to our deep learning model which can give you the good result. And then comes one of the famous stuff, that is social media, maybe Facebook, maybe Instagram, or like that. Okay, maybe Snapchat or anything. They will be having their own filters already available. Okay, but the filters are made like this only. Okay, if you want to build your own social media or like that stuff, you can use this one, where when a person takes a picture you need to ask him whether he want to use this filter for it, if his image is having a darkness behind it, and you will get good result. So these are all the applications, and in some areas it's already available. Maybe in Facebook and Instagram they are already using so many filters, so they are using this technology as one of the filters to their images. First we will see how our dataset actually is. So when we open our dataset we will be having two folders. One is eval and another one is the training dataset which we will use. In eval we have 15 images. Each images for low low light, and another one is for highlight conditions. So you can see here in low folder, if 1.png is having a darkness here, the same stuff, the same image will be having higher darkness 1.png in high folder. It means that is the input and this is the output. For any deep learning model, we should have two things. One is output and the input, both during for training and testing. This our 485, this is a folder that we are going to use for training and testing purpose. Okay, we will check okay how many images from this folder we will going to use for training and for testing, remaining for testing. So when I open this folder, I will be having two subfolders. One is low and one is high. When I open low, 2.png is a dark background image. Okay, so the same image in high will be having clear stuff. So this is all about our dataset. Like this, we have 485 images in one folder, which we actually use for training and testing, and all 15. Those images we will be using for evaluating. Okay. Now we will start with the coding. If you need dataset, just message us or call us to the given number below. Once we provide you the dataset, you can start with the coding. The first part of the coding is the libraries. Here you can see we are importing the basic libraries that we need for our work. The first library which we are using is OS, that is operating system. This is used to access the files in our case. And then random is actually used to generate any random numbers or floats. Then comes a library called numpy, which is used to work with arrays, multidimensional arrays or arrays. Glob is used to access the data from the folder or serialize the data, we can say, from the folder or like that. Then comes a library called pill. Pill is a library which is used to access the images or work on that images using some predefined functions. For example, using image you can import the images. Using image OPS, in our case we are going to increase the contrast of the input image or dark image. During comparison we will use this function. Okay, if you continuously watch this video, you will understand where we are using it and how we are implementing using that stuff. Then comes a library called matplotlib, which we actually using to plot the images or graphs where there are the requirements. Then comes our main library, that is TensorFlow and Keras. Here we are using this to build the deep learning model. Before moving further, we are setting up some basic hyperparameters or some most important variables. So image size, what is the image size that we are going to work on? Our image size we are defining, it will be 256 cross 256 comma 3. That is it is having the shape of 256 with RGB color. Then comes batch size. It depends on you what number of batch size you want to give. What actually batch size is, for example, in my case I have 465 images. Okay, among 465 I may take first 400 images for training. During training, in each epoch, okay, during training in each epoch, how many images together I am feeding for training, that what defines the batch size. Okay, batch size nothing but the bundle of images, how many images you are feeding to the model during the training at once. So it will be normally be multiple of 8, 16, 32, 64 or like that. Okay, it depends on your system and also the maximum number of the images. You can take around 32 or 64. There are some hypotheses where they will define like some bit equations. They say like 10% of training data you should give it as a batch size, or 1% or 5%, like that. So better you can go like this, multiple of it rather than 10%, 20% or like that. No problem at all. I am using 16. You can go with 32 or 64. But this takes a bit more time for training when you increase the number of batch size. But there is a chance of increasing accuracy better than the lower batch size. If you go on increasing a batch size, there is a possibility that you are going to get better accuracy result. Then we are going to set up what is the maximum training image. That is, I'm restricting like from 465 images, how many I should use for training. I'm telling like, okay, I will only use 400 images, remaining 65 images I will use for testing. So that I will define. Okay, for that I'm just defining that variable here. Then now here I need to split the data set. Now for training, how many images I should have, I will use glob for that. I will use glob and I will access that folder, okay, low folder, and I will say it should be from 0 to 400. It's nothing but max train images. Max train images is 400. It means first 400 images are for training, and then the remaining for validation from max train to infinite, that is 400 to 65, 465, that is 65 images are for validation, and for testing we are going to use that evolve folder data. Now we need to generate data from the images that we have. It means we need to convert the images into some numpy or tensorflow arrays. So how we gonna do that? For that I'm going to build a function here, that is data generator. To that I'm going to feed whatever the images I imported. So when I feed that to this data generator function, what will happen? So for that I define two functions here. One is data generator. What it will do is it will take that low light image, each images, okay, then it will come convert them into tensors, and then it will send that image to this load data function. This load data function, it will read the image, it will decode the image, it will resize that image, and then it will normalize the image pixels between 0 and 1. That is normalizing nothing but keep it between 0 and 1, divide each pixel by the maximum pixel value, that is 255. So when it gets back that image as a data set, that data set it gonna batch them 16 like that, like our batch size which we defined was 16. So now it will batch 16 images together and it will return the whole data set back to here. We'll do the same thing for train images and also for validation images. Once we have data ready for us, now we are going to build a deep learning model. For that I am going to first define a function. In that function I will define what are the layers I am going to use. First I am going to take the input image, whatever the input images comes into the model. After that I am going to use convolution 2D layers, multiple convolution 2D layers. The 6 convolution 2D layers I am going to use, okay, and then I will concatenate all of them. Here you can see this is convolution 1, convolution 2, convolution 3, 4, 5 and 6, and it is of batch 32 with a filter size 3x3. You can play with this. You can build your own deep learning model with your own filter size and batch. You can change this 32, okay, as 64 or like that. You can even change the activation layers. Okay, the model which I am using, we call it as a DCE net, okay, which is well experimented and it works very well for low light images to convert it into bright light images. So I'm going with this model structure, okay, we call it as a DCE net. If you want to work with your own deep learning model, that's fine and good. You can experiment it with adding some extra layers or changing the layers, changing the activation functions, okay, and filter size. Once we are done with building our deep learning model, we made it as a function, okay, we will call it below. So now we are going to define 4 type of losses that we want during the training of the model. So we are trying to analyze the model based on those 4 losses. So we are going to create those functions for the losses, different type of losses. These are not available losses. We are going to make some equations. Out of that we will get the information or result. First thing is color consistency loss. What does this do? It will try to tell us color deviation from the enhanced between the original image and the enhanced image. It means here the stuff is very simple. Here it will check what is the difference or what is the variation is there with the real image and that colored image. Okay, we will go with an example. For example, take this is my image. Okay, and okay, this region is red. This is the original image. Okay, real image. Then my model will predict this red area during enhancement some problem happened, and this is some reddish plus little blue. Now we are going to take out the deviation out of it. So we try to take the difference of the pixel color with RGB. We are going to check first what is the difference. R minus R, what is the difference? RG, what is the difference? BR, what is the difference? We will compare these two and we will check what is actually the deviation. Okay, if the deviation is more, then our model is not working that much properly, because it should change only intensity, not much color. So that is our concept. So we are defining it. Here you can see, first we will take mean of that RGB value of that, then we're gonna separate. Okay, 3 means out of the result we'll get red, green and blue. Then we'll take the difference square, that is nothing but square itself. Okay, then we are going to get total difference. We are going to sum up the difference squares together. The stuff is here we are trying to get the difference or the deviations of color from one to other. We are defining this we are taking it one of the parameter to measure. And then comes exposure loss. What does this measure? This will give us what is the average intensity of value of local region and preset value exposed to level. So here what happens is, there is already some light here in this region, there is already some light. In this case, how my model is getting or doing changes in that intensity already available area, or the area which is not like there is no intensity at all, or some darkness. Okay, low intensity and high intensity, it should not work same for all the intensities. For example, if this area is already high intensity, okay, if my model directly increase the intensity without knowing, okay, without finding the distance, then no meaning at all. Our idea is to increase the intensity of the dark area, so that's how we want to measure the model. But in this case, if we are increasing already high intensity area, it's worth nothing. Okay, so this is the difference. That's why we are going to get the distance out of that one. For that we are going to use, we are just passing one filter, average pool 2D filter, and we are getting the difference of the intensities. Again here this is just like a root mean square error like stuff. It means we are getting squared error as an output. And then comes the third loss. We call it as an illumination smoothness loss. It will give us what is the exact relationship between neighboring pixels. It means here if this is green, okay, say it was green, and this is red, my intensity whenever the model predicts or when it need to enhance, it should not enhance green area and red area in the same way. It should know the difference, it should know, then only it can properly enhance the stuff. Okay, even color also matters. For that we are going to use illumination smoothness loss. We are going to check it. And then comes the spatial consistency loss. Spatial consistency loss is actually used to make the difference between enhanced image and the original image in case of the contrast between both of them. As we discussed, previous losses were between colors and pixel relation like that. Even here contrast is taken as the main parameter to measure the loss. Now whatever we discussed, we should use all the losses with the model we defined above, and then we should compile it, and then we should train it. So how we gonna do that? We are doing it one by one. First, for compilation, what are the parameters are there? Okay, we are using Adam optimizer, and then what is the loss, main loss, that is spatial consistency loss. We are taking it as function during for the compilation process. Then here in this function, what we'll do is we will try to enhance the image quality using these functions. Okay, here we are going to extract the image information, and we are going to apply some equations. It means here we are trying to increase the intensity part of the image where we want to enhance that. In the end, we are going to get the enhanced image. So then we are going to take all the losses for our model. Whatever the losses we discussed, we are going to apply that all the losses on the data now. Okay, once we get the image or enhanced image, we are feeding it that output to all these losses one by one. Okay, and we are going to get those loss results: loss color consistency, loss illumination, loss spatial consistency, loss exposure. Then we are going to sum up all of them, and we are going to get total loss that we are going to return. Now for training steps, how many steps are epochs are like that? Okay, you need to define that here. You can do. Okay, once you're done with that, you can even mention testing steps, and you can define in which name the file should be saved. And for loading also, there is a function how you can load the saved model. Okay, now everything is fine. Okay, now we will call that function, above function, and then we will compile. For compilation, we will push some parameters, that learning rate. Okay, and then we are going to train it. Okay, dot fit nothing but we are going to train that model using train data set, and validation data is val data set with epochs. As I mentioned, you should also feed epochs. Here I am giving 100 epochs. You can try more than 100, but 100 is enough. It's giving good results. So then you can plot the model results or history results. Okay, when I done that, I got this result. Okay, now what I should do, I should inference it with some images. For that, I am going to take some images from original images. Okay, that means some original images are low light images as an input to my trained model. That's here. Okay, 0 DCE model. Okay, which is trained now. I'm going to feed that. Once I feed, I'm going to get all this stuff. Why I'm getting three is I'm plotting three images. One is original image, another one is image ops. I think initially I told you why I am using this image OPS. Image OPS is one of the pill function, pill library function, which is a wide range of options for us, but one of them is increase the contrast of an image, like auto contrast. Okay, it will increase the contrast of image automatically. And another thing is our model enhanced image. We are going to plot all three of them together to compare the results. You can use this and you can implement it on any other data set. For example, you can take only medical field data set, you can take only defense field data set, you can take e-commerce field data set. You can train it very well and you can get good results. So this was all about today's class. We will meet in next class. Thank you. Don't forget to subscribe and like our channel. Thank you very much.